Okay, good morning, everyone. Thank you for joining today's presentation. My name is Jiajun Xu. I'm the instructor for this class and also the supervisor for some of the projects here today. So welcome, and today's presentation, we have four group of students who will be presenting their senior capstone project. So the senior capstone project started in fall 2020 and continue on in the spring 2021. So it's almost a 1 year project. And this year we have four groups working on four different projects. The first one, which we'll be presenting next, is a joint project between mechanical engineering and biomedical engineering students. So Omer is a senior student from mechanical engineering, and Monatu is a senior student from biomedical engineering major. And their project title is to design a tremor simulator and a suppressing device. So each of the team here today have about 25 minutes to present their capstone project, and they have about 5 minutes at the end to answer any questions the audience may have. So I would like to request the audience to mute yourself during their presentation. If you have questions, please hold on to the end of their presentation, and you can also more than welcome to type in the chat box if you have any questions for the group, and we will answer them at the end of their presentation. And another thing, just to remind, if you can click the link I'm showing you the this is a web page for all the school of engineering capstone projects. So if you click this one under the mechanical and biomedical engineering senior capstone presentations, this is the evaluation form. Please click that link, and also I will send in through the chat box so you can provide a feedback for each of the group at the end of the presentation. So I don't. Is there any questions from the audience, from the students who about today's presentation? If not, we can just go ahead and start today's presentation. And if you have any questions, feel free to type in the chat box. We'll answer them at the end of this first presentation. I forgot to mention that this group is supervised by jointly by faculty member from mechanical engineering and biomedical engineering. So the supervisors are our Dean Shetty and Dr. Thompson and Dr. Chen. With that, I would like to have the students start to share their slides, and they can start their presentation when they're ready. So Omer and Mulatu, are you ready to share your presentation slides and start your presentation?
Good morning, and yes, we are.
Okay, please go ahead.
Good morning, everyone. I hope everyone is doing okay. My name is Omar Alvarado, and I am an undergrad in mechanical engineering. My colleague is Mulado Pachoro, and also an undergraduate student with a background in biomedical engineering. Today we will present our capstone project on the design of a tremor simulator and suppression device. Our academic advisors are Dr. Devda Shetty, Dr. Chen, and Dr. Thompson. This is the outline for today's presentation. First, we will give a brief background information. Then we will highlight some of the constraints we had. We will discuss the main objective of this project, as well as a mathematical model that we developed. Then we will go over a tremor simulation platform and show a product demonstration. Then we will move on to the tremor suppression aspect of this project, and then our conclusions. So our project focuses on tremors caused by Parkinson's disease. So the main scope was to develop a mechatronic device to minimize these oscillations, especially in the fingers. A lot of research has actually been conducted to find, either invasive or non-invasive solutions, since Parkinson's disease is a progressive, chronic, and the second most common neurological condition. Because 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 of that, there are medication that help control tremors, but they have different negative side effects, and the average cost is about $2,500 per person a year. Um, Patients can also undergo surgery, but the cost can go as high as $100,000. Either way, not everyone is able to afford it, and not all the tremors are very responsive to these techniques. So overall, Parkinson's disease affects a lot of people in different ways. So some patients not only have tremors, they also experience other problems such as balance difficulties, muscle stiffness, and troubles with handwriting. One of many examples is that a patient's check often gets rejected because their signature looks different compared to previous records. Based on the literature review, there are many commercially available products that can, that are primarily developed to control these tremors. But the problem is that most of these devices focus on tremors at the wrist and elbows, and especially for all those tremors that are caused by other neurological conditions, and not so much by Parkinson's disease. So the way some of these devices work is by applying a counter-reacting force to the tremor motion and dissipate that energy. Or in the case of the device shown in Figure A, which was designed by Microsoft, by sending some signals that help stimulate the brain. So these devices, though, based on our literature review, have a 50 to 80% efficiency. And to develop more effective ones, we can further analyze 3D tremor using, there are many techniques and components such as IMUs. In one of the articles, also we found that Parkinsonian tremor motion has a unique frequency pattern, and that the second and the third harmonics are significantly important. And this led to the development of the mathematical model I will talk or discuss later. So throughout this project, we encountered different constraints, including the inability to obtain Parkinsonian tremor data. So actually, we had two options: either recruit patients and collect that tremor data, or collaborate with researchers. But due to ethical and safety concerns, especially for COVID-19, this was infeasible, as we require also approval from the Institutional Review Board. Time was another constraint, so we didn't get to design and develop a hand tremor suppression device. That's will uh, talk about this slide.
Uh, the project objectives. Despite this constraint, we approach this problem by constructing a tremor simulator that we can use to study the behavior of Parkinson's disease, and that we can also use to implement a hand tremor suppression device to minimize tremors in the fingers. And to accomplish this, our objective, it was important to understand the characteristics of Parkinson's disease tremors in fingers and wrists. Design mechanical and electric hardware, as well as the software, the simulator, and change the tremor motion estimation algorithm was also important to design and model a tremor suppression device. Next slide.
So, so the mathematical expression is one of the most of the it's one of the most important aspects of this project. Based on the literature review, like I mentioned, we can model PD tremor motion as a sinusoidal signal with a fundamental frequency, the second and the third harmonics, as well as a white noise component, where the frequency of the fundamental frequency of the second harmonics, as well as the as well as the second and the third harmonics, um, lie within these ranges for resting and postural tremor. And here the amplitude is based on the angular velocity at the MCP joint of the index finger, which is about 58.6 degrees per second. So we use these values that are shown on the on the left hand side to visualize Parkinsonian tremor motion. And so we also do some fast Fourier transform, to validate the frequency components. So here the main idea of this mathematical model is to generate some physical signals on the simulator. This is the tremor simulation and acquisition platform. Mulatsu is going to further discuss that.
Tremor simulation and the acquisition platform. The hand model has many interface ABS 3D printed parts and offers 6 degrees of freedom. 5 of them corresponds to the flexion and extension of the fingers and thumb, and 1 for the abduction and adduction of the thumb. These degrees of freedom allows the hand model to provide more realistic hand movements and more realistic tremor characteristics with respect to the finger digits. We were recommended to implement this commercially available product by researchers from Western University in Canada, and it provides the basic understandings and concepts of multiple engineering disciplines such as mechanical and electrical engineering, as well as computing, programming, robotics, and automation. So it can be used for K-12 outreach programs. Most importantly, through the mechanical and electrical assembly of this device, we were able to understand mechanical design for biomedical or for a medical application. So in this case, this simulator enabled us to collect and demonstrate tremor motion. This picture in the left side shows the complete assembly of the hand and exo hand model. We also attached a flex sensor to validate the generated tremor motion. So we will compare the theoretical and experimental signals. Next slide, please. Here we can see the data and the collection. That is how we can construct and the hand model, and basically shows how the model works. First, we are integrating Arduino Nano, every microcontroller that is provided via a USB cable, and that is connected to our computer communication because it has few pairs with this modulation pin out. We are using an Adafruit 16 channel servo drive that can actuate up to 16 servo motors at the same time. Also here we are using 6 servo motors, 4 for the finger movements and 2 for the thumb movement and rotation. After a given command, the microcontroller receives the analog signal from the 6 potentiometers rated at 10 kilo ohms that are mounted on the XO hand. Then it transfers that data to the servo drive, which actuates the servo motor to make the hand mimic finger movements. We implemented the software of this platform so it can be used for multiple functionalities, such as calibrating the potentiometers and servo motors, collecting tremor motion data, generating signal with similar characteristics to Parkinsonian tremor motion, demonstrating basic hand movements and completing simple tasks such as grasping and holding. Uh, uh, Simply, I don't have the access to show you guys how which one is it, but sensing with a 10 kilo ohms meter, that is a potentiometer that from exo hand. The high level control Arduino Nano, every microcontroller, that's the main brain, and then the power supply is that USB cable that we connected from our computer, and the other one is low level, and then Arduino Fruit channel servo drive. Those are attached or mounted in handy models. Can you go to the next slide? I'm sorry for the quality of the video, but here we have a short demo of the simulator platform. You may not be able to hear it, but basically Olmer is explaining the uh, different functionalities I already mentioned, and basically the way the software is designed, we are using the I don't know web editor. So first we send a command of -99 to the controller. Second, the serial monitor displays 5 different options for which a command value is assigned. Some of these options include potentiometers, which can be used to calibrate the potentiometers and the servo motors. Thirdly, we have the movement with a potentiometer command, which can be used to collect Parkinson digital tremor data after meeting all regulations. And fourth, we have the tremor simulator function that can be used to generate the different tremor motion signals by changing the parameter of the mathematical model. Next, we have the movement sequence. As we see here, command which shows finger movements, and we also included a fifth command to make the handy model mimic our hand movements by using the exo hand contralateral side in the way. This command can be really important if we design the hand model as a prosthesis. This can enable upper limb amputees to complete simple tasks in a way to improve their independence. Olmer can continue.
Sorry. So moving on to the tremor suppression aspect of this project, we were unable to develop a prototype due to time constraints. But there are many approaches that we can use, to design an effective tremor suppression device. I remember Dean Shetty suggested many ideas, especially this noise technology, this noise, I'm sorry, reduction technology that is used in audio systems. So before we build a prototype, we can actually develop a software-based solution that can, be simulated under different conditions. For example, we can use this filter X normalized LMS algorithm shown on the left-hand side. In active noise control, there are multiple algorithms which include the filter X NLMS algorithm and the traditional LMS algorithm, and they all are used in many applications such as air conditioning ducts, washing machines, audio systems, vacuum cleaners, and many other and many more, that require noise control and reduction for higher efficiency. And so the main objective of active noise control is that an anti-noise is introduced and designed to cancel an unwanted noise. This noise can be any disturbance, and for the scope of this project, we can treat it as an unwanted vibration. The reduction of the signal, can occur if the signal and the anti-signal have the same amplitude, but opposite phase. Um, if
You didn't start the project,
if
right?
and just to elaborate
Oh, okay.
elaborate more on this concept. The figure on the left hand side shows a diagram of the active noise control system using the filter X LMS. Here, X of Z is the reference signal that can be used as a primary path. The adaptive filter is added to estimate the primary path and also to minimize the error signal. The LMS, actually, the LMS algorithm control this filter. So over time, the weight coefficients get updated. Here, this block right here represents the secondary path, and it is estimated by adding this filter right here. And so, this algorithm is basically based on the superposition principle. So if this output signal as well as this one are acoustically combined, the error signal will be equal to zero. So, which in many cases, this is what we're looking for. And so, this algorithm has this loop which can be used to minimize residual residual signal. Later here will explain how we use this filter algorithm for our project.
Okay, Omar, I really like to help you with the pointing. And okay, so here on the right hand side, we have an implemented simulink block diagram in which we are applying the filtered X normalized LMS least mean square algorithm. Just like Ulmer explained, for the primary path, we are using the Parkinson-based thermal signal we showed in the mathematical model. This adaptive filter will basically estimate the secondary path, and its accuracy mainly depend on the filter coefficients. Also, here we have the anti-noise, or the signal that will be used to cancel the primary noise source, and it will be used as the secondary path. This anti-noise signal is created by using an additional LMS filter. This junction right here basically will take the uh, difference between the two signals. Also, here a mu is the adaptive step size, and as long as it is small, we can use the traditional LMS algorithm and still get accurate results for the normalized LMS algorithms. So changing it has a much higher influence on the residual signal. Here, this signal generator blocks right here basically are added to show a voluntary hand movement, and the original thermal motion signal without the Gaussian white noise component, and just uh, visualize the system response. There is a lot of math involved in active noise control, especially in these types of algorithm. But the coefficient scope right here shows the coefficients that are updated by the LMS algorithm, and basically here will show the thermal motion signals, especially the one from the primary nodes and the residual signals. Can you go to the next slide? And this picture, the figure on the right hand side shows the scope output after we run the simulation. Basically, it shows a comparison of the noise source signal. In this case, the Parkinson disease tremor signal and the same signal after applying the filtered X normalized LMS, or at least the mean square algorithm. Uh, we can observe that as we run the simulation, the power and the noise of the thermal motion signal is minimized, which is due to the step size as well as the weight coefficients of the estimated second pass transfer function. Also, the figure on the left-hand side shows the updated weight coefficients and how, or shows the amplitude of the residual tremor as we run the simulation. These coefficients are updated by the normalized LMS algorithm. We can alter these coefficients on the secondary path and then conduct frequency domain analysis to determine the amount of thermal reduction. So, uh, as we know, in order for a thermal signal to have a fast convergence, we can create more accurate anti signals. Next slide, please. And the conclusion, you know, for this project, we developed a mathematical model that can be used to describe Parkinsonian postural and resting tremor, and that can be used to generate a physical signal using the tremor simulator. We successfully assembled, troubleshooted, and improved the software of commercially available product, so we can use it in a clinical environment and for other useful purposes. We also implemented a Simulink model diagram that can be used for thermal reduction, and that can help us design a separation device prior to its physical developments. Elmer, can you?
Unfortunately, we there were many things that we were not able to complete. But for our future work, we would like to do some vibration analysis, mainly to determine if the signals that are generated on the simulator match the theoretical ones. And after meeting all regulations, I think it would be important to recruit patients to collect, not only Parkinsonian tremor data, but also tremor data in general. Also, I think it is important to work on the tremor suppression algorithm to develop a prototype, that and then that we can use in parallel with the tremor simulator to determine the effectiveness. And just like Lad mentioned, this project has a lot of engineering concepts, so we can improve this platform.
Here, I like to thanks and our advisors, Dr. Thompson, Dr. Chen, and Dr. Sherry, and the department. Also, the School of Engineering, Catholic University of America, which provide all the 3D printed parts and who help us by funding a National Science Foundation or NIH. Also, Dr. Hans as well, Yuju and Analuz, trees from a Western University of Canada. Those are help us by providing this material and advice. Thank you so much. And this is our references. And if you have a question, please welcome.
Okay, thanks for the presentation. Any questions, comments from the audience? If you're not able to speak directly, you can just type in the chat box.
Yeah, I have a question. This is Dr. Klein. I just wanted you guys maybe to comment on what you found the most challenging aspect of your project and how you were able to overcome some of those challenges.
I guess I can go first. Actually, there were many concepts that seems to be or at least at that time seemed to be kind of complicated, especially for me. I'm a mechanical engineering undergraduate. I'm not familiar with computer programming or microcontroller based programming. So I had some experience. I took microcontrollers. I did the basics. I also remember for the introduction to engineering, we work on similar projects, but it's not like it's not like I personally learned a lot. But with this project, not only programming, we also encounter, with this algorithm. It has we had to control systems also. It gave the fundamental, understandings of this model-based software. But I mean, we had to cope. We had to apply, whatever we had learned, and I guess overall there were also some. I think personally taking courses like automation and automation really. I'm sorry, not automation. Robotics. Just helped me actually for this project.
Okay, thank you. And Bachoro, you as well?
Yeah, mostly our challenge was, especially Olmer addressed the other parties, but because of this COVID, we have a big challenging to accomplish this. But thanks to technology, it helped a lot to share. Whenever when we join together physically and doing something, instead of that, we use technology. But there was a big challenge to accomplish and not to be successful. Main thing is not we cannot get our supervisor physically even to show something that they help us online. So sometimes that make us that is personally it was sometimes hard. Like if we will be for 3D printing or for another things, if we meet in person, that was a big challenging. And the other one is some courses for software develop. It was not in biomedical, but since Olmer is with me, I really happy. So he helped that parties, and then we're doing good. That's all I have.
Okay. Yeah. So if I may ask you another question, just I think you touched a little bit at the beginning. So while you are doing this project, um, did you see any like engineering standards that you have to implement? For example, some specific biomedical standards. When you design this device to meet, to be able to apply, and use for the patients. Is there any? You mentioned some RRB, some other stuff. Um, so I just wonder, what did you have you do any research or come across any of those topics regarding to the engineering standards?
Well, yes, there there are many regulations, especially in uh, you know in I guess in most of engineering applications, right? But especially in biomedical engineering. So since we are working on this project that involves patients, so whenever a person is involved, if we trying to get some type of data and we want to do some testing, we need to go through the institutional review board to get approval. Also, and I guess just to meet certain criteria. For example, is a safety for them or is a safety for us? Then overall, I think this product, especially when if we put it in the market, it has to go through the FDA. And I guess this is what we realized. And also, I think there was another one because we got in contact with research from Western University of Canada, and so they also have done some research on Parkinson's disease. We got to the point that we were discussing, how to collaborate, but time constraint was kind of it was a big challenge, so they had to do some amendments on the protocols.
Okay. All right. Any other questions or comments from the audience? Just a remind, please complete the survey using the link in the chat box. Yes. Was there a question or something?
Dr. Xu, this is Dr. Chen, Dr. Thompson, and Dr. Tan. Yeah, it's I mean, as one advisor for this project, and I think both you and Dr. Khan mentioned about the challenging part of this project. I think because during the pandemic, I think I mean it's definitely initially it's hard to set up the tangible goals for this project, but luckily, I mean coming from this idea of developing a Tremor-based platform, I think we're able to narrow down some tangible goals and also able to deliver those goals. I mean, definitely you can see from the slide of acknowledgement, we have be able to pull out all resources and come together to actually come to this step. I have to say that both students work very hard. And also, I mean, this project itself covers the many aspects of engineering. And as a matter of fact, that's a part of real engineering work. And I think, later on, I mean, the next semester, if there's similar project like that, definitely the students can get a well, well-rounded training in all aspects of engineering. So, yeah, I just want to comment on that. Yeah.
Okay, thanks for mentioning that.